Openstax Contemporary Mathematics, Chapter 2, Chapter 2, Logic. Figure 2.1. Logic is key to a well-reasoned argument in both math and law. Credit. And shows a Lady of Justice and a gavel with a little gavel smasher. Chapter outline. 7 sections. 2.1. Statements and quantifiers. 2.2. Compound statements. 2.3. Constructing truth tables. 2.4. Truth tables for the conditional and biconditional. 2.5. Equivalent statements. 2.6. De Morgan's laws. 2.7. Logical arguments. Introduction. What is logic? Logic is the study of reasoning, and it has applications in many fields, including philosophy, law, psychology, digital electronics, and computer science. In law, constructing a well-reasoned, logical argument is extremely important. The main goal of arguments made by lawyers is to convince a judge and jury that their arguments are valid and well supported by the facts of the case, so the case should be ruled in their favor. Think about Thurgood Marshall arguing for desegregation in front of the U.S. Supreme Court during the Brown versus Board of Education of Topeka lawsuit in 1954, or Ruth Bader Ginsburg arguing for equality in Social Security benefits for both men and women under the law during the mid-1970s. Both these great minds were known for the preparation and thoroughness of their logical legal arguments, which resulted in victories that advanced the causes they fought for. Thurgood Marshall and Ruth Bader Ginsburg would later become well-respected justices on the U.S. Supreme Court themselves. In this chapter, we will explore how to construct well-reasoned logical arguments using varying structures. Your ability to form and comprehend logical arguments is a valuable tool in many areas of life. Whether you're planning a dinner date, negotiating the purchase of a new car, or persuading your boss that you deserve a raise. 2.1. Statements and quantifiers. Figure 2.2. Construction of a logical argument, like that of a house, requires you to begin with the right parts. Credit. Shows a picture of the frame of the house. Learning objectives. After completing this section, you should be able to 1. Identify logical statements. 2. Represent statements in symbolic form. 3. Negate statements in words. 4. Negate statements symbolically. 5. Translate negations between words and symbols. 6. Express statements with quantifiers of all, some, and none. 7. Negate statements containing quantifiers of all, some, and none. Have you ever built a clubhouse, treehouse, or fort with your friends? If so, you and your friends likely started by gathering some tools and supplies to work with, such as hammers, saws, screwdrivers, wood, nails, and screws. Hopefully at least one member of your group had some knowledge of how to use the tools correctly and helped to direct the construction project. After all, if your house isn't built on a strong foundation, it will be weak and could possibly fall apart during the next big storm. The same foundation is important in logic. In this section, we will begin with the parts that make up all logical arguments. The building block of any logical argument is a logical statement, or simply a statement. A logical statement has the form of a complete sentence, and it must make a claim that can be identified as being true or false. When making arguments, sometimes people make false claims. When evaluating the strength or validity of a logical argument, you must also consider the truth values, or the identification of true or false, of all the statements used to support the argument. While a false statement is still considered a logical statement, a strong logical argument starts with true statements. Identifying logical statements. Figure 2.3. Not all roses are red. Credit. Shows a picture of roses of different colors. An example of logical statement with a false truth value is, all roses are red. It is a logical statement because it has the form of a complete sentence and makes a claim that can be determined to be either true or false. It is a false statement because not all roses are red. Some roses are red, but there are roses that are pink, yellow, and white. Requests, questions, or directives may be complete sentences, but they are not logical statements because they cannot be determined to be true or false. For example, suppose someone said to you, "Please sit down over there." This request does not make a claim, and it cannot be identified as true or false. Therefore, it is not a logical statement. Example 2.1. Identifying logical statements. Determine whether each of the following sentences represents a logical statement. If it is a logical statement, determine whether it is true or false. 1. Tiger Woods won the Masters Golf Championship at least 5 times. 2. Please sit down over there. 3. All cats dislike dogs. Solution. 1. This is a logical statement because it is a complete sentence that makes a claim that can be identified as being true or false. As of 2021, this statement is true. Tiger Woods won the Masters in 1997, 2001, 2002, 2005, and 2019. 2. This is not a logical statement because although it is a complete sentence, this request does not make a claim that can be identified as being either true or false. 3. This is a logical statement because it is a complete sentence that makes a claim that can be identified as being true or false. This statement is false because some cats do like some dogs. Your turn 2.1. Determine whether each of the following sentences represents a logical statement. If it is a logical statement, determine whether it is true or false. 1. The Buffalo Bills defeated the New York Giants in Super Bowl 25. 2. Michael Jackson's album Thriller was released in 1982. 3. Would you like some coffee or tea? Representing statements in symbolic form. When analyzing logical arguments that are made of multiple logical statements, symbolic form is used to reduce the amount of writing involved. Symbolic form also helps visualize the relationship between the statements in a more concise way in order to determine the strength or validity of an argument. Each logical statement is represented symbolically as a single lowercase letter, usually starting with the letter P. To begin, you will practice how to write a single logical statement in symbolic form. This skill will become more useful as you work with compound statements in later sections. Example 2.2. Representing statements using symbolic form. Write each of the following logical statements in symbolic form. 1. Barry Bonds holds the Major League Baseball record for total career home runs. 2. Some mammals live in the ocean. 3. Ruth Bader Ginsburg served on the U.S. Supreme Court from 1993 to 2020. Solution. 1. P. Barry Bonds holds the Major League Baseball record for total career home runs. The statement is labeled with a P. Once the statement is labeled, use P as a replacement for the full written statement to write and analyze the argument symbolically. 2. Q. Some mammals live in the ocean. The letter Q is used to distinguish this statement from the statement in question 1, but any lowercase letter may be used. 3. R. Ruth Bader Ginsburg served on the U.S. Supreme Court from 1993 to 2020. When multiple statements are present in later sections, you will want to be sure to use a different letter for each separate logical statement. Your turn 2.2. Write each of the following logical statements in symbolic form. 1. The movie Gandhi won the Academy Award for Best Picture in 1982. 2. Soccer is the most popular sport in the world. 3. All oranges are citrus fruits. Who knew? Mathematics is not the only language to use symbols to represent thoughts or ideas. The Chinese and Japanese languages use symbols known as Hanzi and Kanji, respectively, to represent words and phrases. At one point, the American musician Prince famously changed his name to a symbol representing love. And then there's a BBC Prince symbol article. Negating statements. Consider the false statement introduced earlier. All roses are red. If someone said to you, all roses are red, you might respond with, some roses are not red. You could then strengthen your argument by providing additional statements such as, there are also white roses, yellow roses, and pink roses, to name a few. The negation of a logical statement has the opposite truth value of the original statement. If the original statement is false, its negation is true, and if the original statement is true, its negation is false. Most logical statements can be negated by simply adding or removing the word not. For example, consider the statement, Emma Stone has green eyes. The negation of this statement would be, Emma Stone does not have green eyes. The table below gives some other examples. Here's table 2.1. Logical statement, Gordon Ramsay is a chef. The negation, Gordon Ramsay is not a chef. Logical statement, Tony the Tiger does not have spots. Negation, Tony the Tiger has spots. The way you phrase your argument can impact its success. If someone presents you with a false statement, the ability to rebut that statement with its negation will provide you with the tools necessary to emphasize the correctness of your position. Example 2.3. Negating logical statements. Write the negation of each logical statement in words. 1. Michael Phelps was an Olympic swimmer. 2. Tom is a cat. 3. Jerry is not a mouse. Solution. 1. Add the word not to negate the affirmative statement. Michael Phelps was not an Olympic swimmer. 2. Add the word not to negate the affirmative statement. Tom is not a cat. 3. Remove the word not to negate the negative statement. Jerry is a mouse. Your turn 2.3. Write the negation of each logical statement in words. 1. Ted Cruz was not born in Texas. 2. Adele has a beautiful singing voice. 3. Leaves convert carbon dioxide to oxygen during the process of photosynthesis. Negating logical statements symbolically. The symbol for negation or not in logic is the tilde. So not P is represented as tilde P. To negate a statement symbolically, remove or add a tilde. The negation of not P, is P. Symbolically, this equation is tilde, and then in parentheses, tilde P, which equals P. Example 2.4. Negating logical statements symbolically. Write the negation of each logical statement symbolically. 1. P. Michael Phelps was an Olympic swimmer. 2. R. Tom is not a cat. 3. Tilde Q. Jerry is not a mouse. Solution. To negate an affirmative logical statement symbolically, add a tilde, so tilde P. 2. Because the symbol for this statement is R, its negation is tilde R. 3. The symbol for this statement is tilde Q, so then to negate it, we simply remove the tilde because tilde Q is Q. The answer is Q. Your turn 2.4. Write the negation of each logical statement symbolically. 1. Tilde P. Ted Cruz was not born in Texas. 2. Q. Adele has a beautiful voice. 3. R. Leaves convert carbon dioxide to oxygen during the process of photosynthesis. Translating negations between words and symbols. In order to analyze logical arguments, it is important to be able to translate between the symbolic and written forms of logical statements. Example 2.5. Translating negations between words and symbols. Given the statements, R. Elmo is a red Muppet. P. Ketchup is not a vegetable. 1. Write the symbolic form of the statement, Elmo is not a red Muppet. 2. Translate the statement, tilde P, into words. Solution. 1. Elmo is not a red Muppet is a negation of Elmo is a red Muppet, which is represented as R. Thus, we would write Elmo is not a red Muppet symbolically as tilde R. 2. Because P is the symbol representing the statement, ketchup is not a vegetable, tilde P is equivalent to the statement, ketchup is a vegetable. Your turn 2.5. Given the statements, R, Woody and Buzz Lightyear are best friends, and tilde P, Wonder Woman is not stronger than Captain Marvel. 1. Write the symbolic form of the statement, Wonder Woman is stronger than Captain Marvel. 2. Translate the statement, tilde R, into words. Expressing statements with quantifiers of all, some, or none. A quantifier is a term that expresses a numerical relationship between two sets or categories. For example, all squares are also rectangles, but only some rectangles are squares, and no squares are circles. In this example, all, some, and none are quantifiers. In a logical argument, the logical statements made to support the argument are called premises, and the judgment made based on the premises is called the conclusion. Logical arguments that begin with specific premises and attempt to draw more general conclusions are called inductive arguments. Consider, for example, a parent walking with their 3-year-old child. The child sees a cardinal fly by and points it out. As they continue on their walk, the child notices a robin land on top of a tree and a duck flying across to land on a pond. The child recognizes that cardinals, robins, and ducks are all birds, then excitedly declares, "All birds fly." The child has just made an inductive argument. They noticed that 3 different specific types of birds all fly, then synthesized this information to draw the more general conclusion that all birds can fly. In this case, the child's conclusion is false. The specific premises of the child's argument can be paraphrased by the following statements. 1. Premise: cardinals are birds that fly. 2. Premise: robins are birds that fly. 3. Premise: ducks are birds that fly. The general conclusion is all birds fly. All inductive arguments should include at least 3 specific premises to establish a pattern that supports the general conclusion. To counter the conclusion of an inductive argument, it is necessary to provide a counterexample. The parent can tell the child about penguins or emus to explain why that conclusion is false. On the other hand, it is usually impossible to prove that an inductive argument is true, so inductive arguments are considered either strong or weak. Deciding whether an inductive argument is strong or weak is highly subjective and often determined by the background knowledge of the person making the judgment. Most hypotheses put forth by scientists using what is called the scientific method to conduct experiments are based on inductive reasoning. In the following example, we will use quantifiers to express the conclusion of a few inductive arguments. Example 2.6. Drawing general conclusions to inductive arguments using quantifiers. For each series of premises, draw a logical conclusion to the argument that includes one of the following quantifiers: all, some, or none. 1. Squares and rectangles have 4 sides. A square is a parallelogram, and a rectangle is a parallelogram. What conclusion can be drawn from these premises? 2. 1 plus 2 equals 3, 6 plus 7 equals 13, and 23 plus 24 equals 47. Of these, 1 and 2, 6 and 7, and 23 and 24 are consecutive integers. 3, 13, and 47 are odd numbers. What conclusion can be drawn from these premises? 3. Sea urchins live in the ocean, and they do not breathe air. Sharks live in the ocean, and they do not breathe air. Eels live in the ocean, and they do not breathe air. Typo. What conclusion can be drawn from these premises? Solution. 1. The conclusion you would likely come to here is some 4-sided figures are parallelograms. However, it would be incorrect to say that all 4-sided figures are parallelograms because there are some 4-sided figures, such as trapezoids, that are not parallelograms. This is a false conclusion. 2. From these premises, you may draw the conclusion all sums of 2 consecutive counting numbers result in an odd number. Most inductive arguments cannot be proven true, but several mathematical properties can be. If we let n represent our first counting number, then n plus 1 would be the next counting number, and n plus 1 equals 2n plus 1, because 2n is divisible by 2. It is an even number, and if you add 1 to any even number, the result is always an odd number. Thus, the conclusion is true. 3. Based on the premises provided with no additional knowledge about whales or dolphins, you might conclude no creatures that live in the ocean breathe air. Even though this conclusion is false, it still follows from the known premises and thus is a logical conclusion based on the evidence presented. Alternatively, you could conclude some creatures that live in the ocean do not breathe air. The quantifier you choose to write your conclusion with may vary from another person's based on how persuasive the argument is. There may be multiple acceptable answers. Your turn 2.6. For each series of premises, draw a logical conclusion to the argument that includes one of the following quantifiers: all, some, or none. 1. 1 plus 2 equals 3, 5 plus 6 equals 11, and 14 plus 15 equals 29. Of these, 1 and 2 are consecutive integers, 5 and 6 are consecutive integers, and 14 and 15 are consecutive integers. Also, their sums, 3, 11, and 29, are all prime numbers. Prime numbers are positive integers greater than 1 that are only divisible by 1 and the number itself. What conclusion can you draw from these premises? 2. A robin is a bird that lays blue eggs. A chicken is a bird that typically lays white and brown eggs. An ostrich is a bird that lays exceptionally large eggs. If a bird lays eggs, then they do not give live birth to their young. What conclusion can you draw from these premises? 3. All parallelograms have 4 sides. All rectangles are parallelograms. All squares are rectangles. What additional conclusion can you make about squares from these premises? Caution. It is not possible to prove definitively that an inductive argument is true or false in most cases. Negating statements containing quantifiers. Recall that the negation of a statement will have the opposite truth value of the original statement. There are 4 basic forms that logical statements with quantifiers take on. 1. All A are B. 2. Some A are B. 3. No A are B. And 4. Some A are not B. The negation of logical statements that use the quantifier all, some, or none is a little more complicated than just adding or removing the word not. For example, consider the logical statement, all oranges are citrus fruits. This statement expresses as a subset relationship. The set of oranges is a subset of the set of citrus fruit. This means that there are no oranges that are outside the set of citrus fruit. The negation of the statement would have to break the subset relationship. To do this, you could say, at least one orange is not a citrus fruit, or more concisely, some oranges are not citrus fruit. It is tempting to say, no oranges are citrus fruit, but that would be incorrect. Such a statement would go beyond breaking the subset relationship to stating that the two sets have nothing in common. The negation of A is a subset of B would be to state that A is not a subset of B, as depicted by the Venn diagram in Figure 2.4. So we have 2 little Venn diagrams, Figure 2.4. The rectangle is blue, U equals fruit. See, and then there's a green circle, or I guess it's kind of like a yellowish circle, and that's the set of oranges. Oh, sorry. The bigger circle is citrus fruit. The smaller circle within the bigger circle, so it's like nested in there, with a subset, is oranges. And it's completely inside when oranges is a subset of citrus fruit. But when oranges is not a subset of citrus fruit, then the circle contains an area that exists outside. I guess that's proper subset. Part of the little circle, oranges, will exist outside of the citrus fruit circle. The statement, all oranges are citrus fruit, is true, so its negation, some oranges are not citrus fruit, is false. Now consider the statement, no apples are oranges. This statement indicates that the set of apples is disjointed from the set of oranges. The negation must state that the two are not disjoint sets, and that the two sets have at least one member in common. Their intersection is not empty. The negation of the statement, A intersection B is the empty set, is the statement, A intersection B is not empty, as depicted by the Venn diagram in Figure 2.5. So we have Figure 2.5. We have the statement and the negation. So it's the same, U equals fruit, but apples and oranges are 2 circles separated and disjoint. And that's when apples intersect oranges is the empty set. And then when apples intersects oranges is not the empty set, both the circles actually merge and there are points in common. The negation of the true statement, no apples or oranges, is the false statement, and some apples are oranges. Okay, Table 2.2 summarizes the 4 different forms of logical statements involving quantifiers and the forms of their associated negations, as well as the meanings of the relationships between the 2 categories of set A and B. So we have Table 2.2, logical statements with quantifiers. So the form, all A or B, means A is a subset of B, and so all zebras have stripes, which is true. The negation of the logical statement, so you have form, some A are not B, means A is not a subset of B. Some zebras do not have stripes, which is false. Next, we have the logical statement, form, some A are B, means A intersection B is not empty. So A intersect B is not the empty set. Some fish are sharks, which is true. The negation, the form, no A are B, means A intersection B is empty. So A intersect B is the empty set. No fish are sharks, which is false. Next logical statement, form, no A are B, means A intersection B is empty. No trees are evergreens, which is false. And then the negation, form, some A are B, means A intersection B is not empty. some trees are evergreens, which is true. Logical statement, form some A are not B, means A is not a subset of B. Some horses are not Mustangs, which is true. And then the logical negation, form all A are B, means A is a subset of B. All horses are Mustangs, which is false. We covered sets in great detail in Chapter 1. To review, A is a subset of B. It means that every member of set A is also a member of set B. The intersection of two sets A and B is the set of all elements that they share in common. If A intersection B is the empty set, then sets A and B do not have any elements in common. The two sets do not overlap. They are disjoint. Video. Logic Part 1A. Logic statements and quantifiers. Example 2.7. Negating statements containing quantifiers all, some, or none. Given the statements, P, all leopards have spots, R, some apples are red, S, no lemons are sweet, write each of the following symbolic statements in words. 1, tilde P, 2, tilde R, 3, tilde S. Solution. 1. The statement all leopards have spots as P has the form all A are P. According to Table 2.2, the negation will have the form some A are not P. The negation of P is the statement some leopards do not have spots. 2. The statement some apples are red has the form some A are B. This indicates that the categories A and B overlap or intersect. According to Table 2.2, the negation will have the form no A are B, indicating that A and B do not intersect. This results in the opposite truth value of the original statement. So the negation of some apples are red is the statement no apples are red. 3. Because S is the statement no lemons are sweet, S is asserting that the set of lemons does not intersect with the set of sweet things. The negation of S, tilde S, must make the opposite claim. It must indicate that the set of lemons intersects with the set of sweet things. This means at least one lemon must be sweet. The statement some lemons are sweet is tilde S. The negation of the statement no A are B is the statement some A are B, as indicated in Table 2.2. Your turn 2.7. Given the statements tilde P, some apples are not sweet, R, no triangles or squares, S, some vegetables are green, write each of the following symbolic statements in words. 1, P, 2, tilde R, 3, tilde S.